Hi dear students. So in the last lecture we have discussed about the concept of the kinetic energy and as well the work energy theorem. So in this section we will discuss about the concept of the potential energy. So simply the energy stored in a body due to its position is known as the potential energy. Otherwise the measurement of the ability of a body to do work due to the virtue of its position. That is known as that amount is known as the potential energy stored in the case of that particular body. So let us consider a ball is raised up to a height of h. The work done by the external agency against the gravitational force is actually mgh. That means when the ball reaches a height of h, the stored energy in the ball is equal to mgh, where that is mg is the force acted upon the ball by the gravitational force. Mass, where g is the acceleration, and the displacement occurred it is h. So m into g into h. So this energy is actually equal to the work done by the external force to bring the ball from height 0 to height h. So this work gets stored as a potential energy in the ball. So the gravitational potential energy of an object as a function of height h is denoted by the V of h, where the term V is representing the potential energy, and as a subscript you are having the h, that is h is indicating the height or the displacement occurred. And where the potential energy is actually the negative work done by the gravitational force in raising the object to that height. Actually g value it is always considered as negative, minus. The movement is upward and the gravitational acceleration is acting downwards. So taking the g value as negative, then the negative of the work done by the gravitational force will be equal to minus of minus mgh. That is mgh. This mgh is actually equal to the potential energy stored in one particular body at a height of h. Okay. Now, if you are considering the h as a variable where the mass value and the gravitational acceleration values are same throughout the time, but if the body is moving, then the h is a variable along with the time. Then considering this as a variable, then the gravitational force F equals to negative of the derivative of V of h with respect to h. That is, gravitational force is equal to minus of d by dh of V of h, where which is equal to minus m into g into dh by dh, that is minus m into g. The gravitational force upon a body will be equal to minus m into g, where m is the mass of the body and g is the gravitational acceleration of the particular body. Now here the negative sign indicates that the gravitational force is acting downwards, or the gravitational acceleration is acting downwards, but the movement is towards the upward. Okay, movement is upwards. From the kinematic equation, the velocity of the freely falling body just before hitting the ground will be equal to, for a freely falling body, the kinematic equation, if you are applying, that is will be equal to v square is equal to 2gh, where you are using the v square is equal to u square minus 2as, where a value it is actually equal to minus g, so minus g into minus the plus g ho jayega, that will become the plus g, so that is 2g, where yes, the displacement is actually the height, so h 2gh, so v plus 2gh is actually the u square plus 2gh is actually v square, where u square is actually 0, so the v square will be equal to 2 into g into h. So now substituting or multiplying either side, each side of the v square is equal to 2gh, its equation by with the help of half m, then you can obtain the half m v square is equal to mgh, where half m v square is the kinetic energy at the point just before the collision. Okay, at a point on the near the ground just before the collision, that is the velocity at that point is equal to v. So the kinetic energy value will be half mv square, and mgh, where h is the maximum height and mgh is actually the potential energy stored in the particular body at the height h. So the kinetic energy at the lowermost point is equal to the potential energy at the highest peak or highest point. Okay, in the case of a system. So the gravitational potential energy of the object at height h, when the object is released, manifests itself as kinetic energy of the object on reaching the ground. So the potential energy value will be get converted into the kinetic energy as it is falling freely, and as the body reaches the ground, just before the ground, the kinetic energy value, that is half mv square, will be exactly equal to the mgh, the potential energy stored in the body at the maximum height. So where you know that f of x is equal to minus of dv by dx. It is f of h is equal to minus of dv by dh. So negative integral of the potential energy will be equal to the force. So f of x is equal to minus dv by dx. As you are integrating the both sides, we will obtain the integration of xi to x of f of x dx is equal to minus of integral v of vi to v of dv. That is minus of integral v of vi to v of means equal to vi minus vf. vi minus vf. So the integration of the gravitational force, if you know the value of gravitational force, the direction will be from that means the vi minus vf is actually the initial and the final potential energy values. So difference between the initial and final potential energy values will be equal to the work done, where fx dx is actually the work done by the gravitational force. fx dx, integral f of x dx is actually the work done value, isn't it? Now the work done by a conservative force such as gravity depends on the initial and final positions only, initial and final points only. If the work done is done by a conservative force, where the gravitational force is conservative, So we have to consider only the initial and final points. Okay, in between whatever the things happening, we don't want to consider only the initial Vi and final Vf. We have to consider only these 2 points. If an object of mass m is released from rest from the top of a smooth, frictionless, inclined plane of height h, its speed at the bottom is 2gh, or the root 2gh. That means you can compare the half mv square is equal to mgh, on half mv square on both sides m are there, you can cancel, and 2 you have to consider the 2, or you have multiplying the throughout the equation with the 2, then it will become 2gh. 2gh is equal to v square, so v is equal to root of the 2gh. Okay, irrespective of the angle of inclination, thus the bottom of the inclined plane is acquires a kinetic energy mgh. So the kinetic energy value at the bottommost portion will be just before hitting the ground will be is equal to the potential energy stored in the highermost point, that is half mv square will be is equal to m into g into h. So from that equation we are deriving, that is the force value will be is equal to the change in potential energy of initial and final points. Okay, so the work done or the kinetic energy did depend on other factors such as the velocity or the particular path taken by the object. Then you have to consider the force would be as a non-conservative one. If the work done is not depending only upon the initial and final points, then the force is not conservative. That means the force is depending not only the initial and the final points, it depends upon throughout the, or depending upon throughout the path. Okay, now come to the dimension of the potential energy. The dimension of the potential energy is actually ml squared t raised to minus 2, that is of the kinetic dimension of the kinetic energy. Potential energy, kinetic energy, all those values are having the dimension same, and that unit it is actually joule. So here in the case of the kinetic energy, you have seen that the work done or the change in kinetic energy is actually the work done. Okay, here the change in potential energy will be equal to the negative of the change in work, or the negative of the work done, that is actually the potential energy. And in the case of the kinetic energy, the work done was equal to the potential energy variation or the change in potential energy. Now let us come to the conservation of the mechanical energy. Suppose a body undergoes a displacement delta x under the action of a conservative force. Well, conservative force in the sense the force value, the work done by this force value will be depending only upon the initial and the final points. Okay, in between whatever the value is happening or whatever the thing is happening, you don't want to consider, so only the initial and final points. The force acting, the work done by the force acting is only depending upon the initial and final points. So here as the work energy theorem, from the work energy theorem you can assume or derive that a kinetic energy change delta k is equal to f of x dx. And now only we have derived in the terms of potential energy. The potential energy variation is actually is equal to minus delta v is actually is equal to f of x delta x. So you can see f of x delta x, that is equal in both the RHS, but on LHS the f of delta k and minus delta v are given. That means delta k and minus delta v are equal in magnitude and opposite in equal in magnitude, but a negative sign should be there in the case of the delta v. Okay, So the above equation implies that if you are taking the summation of the delta K and delta V, the change in kinetic energy and the change in potential energy, if you are taking the sum of the delta K and delta K will be, delta V will be is equal to 0. That means delta of the K plus V is equal to 0, as the delta K is equal to minus delta V, delta K plus delta V or delta of K plus V is equal to 0, and K plus V, the sum of the kinetic energy and potential energy of the body, is constant over the whole path, that is xi to xf. This means Ki plus Vxi is equal to Kf plus Vxf. The kinetic energy at the initial point plus the potential energy at the initial point is equal to kinetic energy at the final point plus potential energy at the final point. The quantity K plus V of x is called the total mechanical energy. The sum of potential and the kinetic energy is known as the mechanical energy. So throughout the system, if the force acting upon the particular body, if it is conserved, the kinetic energy, or we can say the sum of kinetic energy and the potential energy, that is the mechanical energy, throughout the path will be get conserved. Okay. Now, the total mechanical energy of the system is conserved if the force doing work on it are conservative. The force should be conservative, then only we can say the mechanical energy is getting conserved, or mechanical energy is conserved. And as well, the force f of x is conservative, it can be derived from the scalar quantity v of x. So the conditions of the conservative force, it should be derived from a scalar quantity. You know that f of x can be derived as the v of x divided by dx. Minus of v of x divided by dx is actually the f of x. So it can be derived from a scalar quantity. So in such forces are known as, such forces are under the category of the conservative force. And the next one, the work done by the conservative force depends only on the end points, initial and the final points. Okay. This can be seen from the relation W is equal to Kf minus Ki, which is equal to V of xi minus V of xf, which depends on the endpoints. And as well, the work done by a conservative force in a closed path is 0. So if you are considering a circular path where the work done will be, that means the initial and the final points are same only, hence the work done will be is equal to, the conservative force will be is equal to 0. Now let us consider the conservation of potential energy to kinetic energy for a ball of mass m dropped from a height h. So observe the figure. You can see the initial velocity is equal to v0. In between one point you are considering where it is small h distance from the ground. So where the velocity of the ball is considered as v is equal to v small h and capital H is the initial height. And at the final, just before hitting the ground, the velocity of the ball is considered as Vf. So V is equal to V0, V is equal to small Vh at a height of h, and as well V is equal to Vf just before hitting the ground, and h is the initial height. These are the values that you have to consider and remember. So the total mechanical energy E0, EH and E capital H. E0 is at the initial position, that is at a height. Sorry, E0 is a ground point just before hitting the ground. E small h is the energy at a point a height of small h, and E capital H is the energy at the mechanical energy at the point of height capital H. Okay, and before that one, the height at small h. Okay, of the ball at the indicated height 0, ground level, h and capital H. H and H are the other height. So we are considering the ground level, height of small h, and height of capital H. So at the height of capital H, the energy stored in the, or energy will be only the potential energy. Maximum potential energy will be there on the initial or the V or the capital H height. So where the value of the potential energy will be equal to m into g into capital H. Now let us come to a height of small h, where the total energy will be equal to mgh plus half of mvh square, because at the highermost point, capital H, there will be no kinetic energy values. Kinetic energy is 0, and the potential energy value will be maximum, and that you can derive with the help of the m into g into capital H. Now coming to one another point where the value in between the path, where the kinetic energy and potential energy values both will be there, but their sum will be equal to the total energy. Okay, so mgh plus half mvh square is the energy at the point height h. Now come to a point just above the ground, where it is going to, where the ball is going to hit the ground, where the potential energy will be equal to, considered to be 0, and the kinetic energy will be the maximum, and the value will be half of m vf square. Vf is final velocity, vh is in between path for height h, the velocity, and the constant force is a special case of spatially dependent force Fx, hence the mechanical energy is conserved. In the case of the constant force or the conserved force, the mechanical energy is conserved. So we can say EH is equal to E0. That means the mechanical energy, total energy at height of capital H, and total energy at the height of 0, where the total energy in the capital H, where it is equal to the potential energy, because the kinetic energy is 0 at the capital H, and the lowermost portion just before hitting the ground, the potential energy will be 0, and the kinetic energy will be there. That is half Vm Ef V half m Vf square. So we can say the mgh will be equal to half of mvf square. This equation. From that one, from this relation, you can derive the Vf, final velocity, as a root 2gh. So same way, if you are considering a height of EH, where capital EH value will be equal to, the capital EH value will be equal to EH, that is the force acting, it is conservative, hence the mechanical energy throughout the points will be equal to a constant. So applying this rule, we can say the VH at a height of small h, that is VH square, is equal to 2 into g into the height, that is h minus h, not the height, the depth, the displacement occurred. Okay, it is a capital H minus h is actually this distance, capital H minus h. This is actually the displacement occurred. This is actually the displacement occurred by the time when it is reaching a height of small h. Okay. So the height capitalized, the energy is purely potential, and it is partially converted to the kinetic energy at a smallest height, and it is completely converted into the kinetic energy by just before hitting the ground, or before we can say at a E0. This is known as the conservation of the energy, mechanical energy. Mechanical energy is actually the sum of the kinetic and potential energy. Okay. So go through the textbook, read the textbook very well, and study these portions, and especially the last topic that we have discussed, that is the conservation of mechanical energy for a free falling body, and the relation or the equation to find out the Vf value, final velocity. Study this derivation clearly, thoroughly. Okay. Thank you.